polynomials in this video. We do have the utilization of Desmos.com, but there are some questions within the lab that are going to ask you about parts of the graphing process. So we do want to review how you would graph if you were not utilizing technology. So we're going to look at graphing formulas in that polynomials in a specific form with parent functions. We're going to graph general functions that are in different forms. We're going to look at the intermediate value and the boundness theorems. Then we're going to approximate the zeros using a graphing calculator, which we're going to use Desmos.com, so it's a free alternative. And then we're going to briefly look at polynomial functions to model data. So if I wanted to graph negative x to the fourth, I could roll over to Desmos.com, type in y equals x to the negative fourth, and I could look at some specific points on the graph to be able to graph it. If I was not using Desmos.com, I would want to strip it down to the bare bones of what is the highest exponent with no number in front, just plain old graph, and that would be x to the fourth. Then I could create a table of values, plot my points, and connect them. Because it's x to the fourth, it's going to be a form of a parabola. Now again, you are encouraged to use Desmos.com in my class, and then if I was going into the lab to graph this, I would look at the x and the y intercepts on Desmos. I would put my point at 0. I'd put a point on the curve, so these right here at negative 16 are right on 2 and negative 2, so that's where I would choose to put those other 2 points to be able to get that parabola drawn. So this is kind of an idea of the characteristics. If my a value is going to be greater than 1, so the number in front of my leading term, it's going to stretch it vertically, which would be imagining pulling a rubber band taller, which makes that rubber band skinnier and skinnier. If the value is between 0 and 1, I am shrinking the rubber band, making it more broad or more fat. If I put a negative in front, that's going to reflect it across the x-axis. If I add a value outside of the variable, it's going to go up or down. If I subtract inside the parentheses, so I'm subtracting directly from x, I would move left or right. Remember, that does move opposite. So if you're subtracting, you're moving right. If you're adding, you're moving left. So if I look at this, I could easily type this into Desmos and to get the graph, but the parent function for this would be considered x cubed, because that is my highest exponent with just a variable. What have I done with x cubed here? I've shifted it 2 to the left, and I've also made it's between 0 and 1, so I've made it more broad or more fat. Now in the lab, it's really hard to understand that, so you would use the cubic function, and you would plot the number of points needed to actually connect the cubic. If I want to graph general polynomial functions, again, we have Desmos.com, but I just wanted to give you a couple of inputs here to what it looks like. If I have an odd exponent, my highest exponent is odd, I'm going to get this cubic look. As I start getting to larger exponents, like x to the fifth and x to the seventh, they're still going to have the same behavior where one side is going up and one side is going down. So see, this side's going down, this side's going up, but there might be more humps connecting those 2 points. So in even functions, both sides are either going to go up or they're going to go down as the function continues forever. The larger that exponent gets, the more humps we're going to have to connect in that situation. Now, multiplicities of a 0 is asked a lot in the lab. If I have x minus 2, at 2, it will cross the axis. If I have x minus 2 squared, it will not cross the axis, it will just be tangent at 2. If I have cubed, it's going to cross the axis, but it's going to have this nice tangent curvature. So in the lab, it's going to ask you, for what values does it cross the axis when it's in factored form? It would cross anywhere the multiplicity of the exponent, like x minus 2, is 1. If the exponent is 2, so if I have x minus 2 squared, it's not going to cross the axis. And the same thing applies for cubed. It will cross, but it's going to be tangent. So turning points are points where the graph literally takes a turn. So in a cubic, imagine this right here is a cubic. That middle point in the cubic is a turning point because I'm going down on one side and then I stop and I'm going up on the other. So that has to do with end behavior. If the number in front of my cubic is going to be greater than 0 or positive, it's going to go from the bottom of the graph to the top as I'm going left to right. If the number in front is negative, it's going to be going down as I go left to right. If I have a quadratic and the number is positive, both ends are going to go up. There might be more humps connecting them, but they're both going to go up. If the number in front of the exponent is negative, both sides are going to go down. And you can verify this in Desmos.com. If I'm graphing a polynomial function, the first thing I'm going to do is plot my zeros in the x-axis. Then I'm going to plot the y-intercept. So even if you're using Desmos.com to graph, you're going to look at the graph on Desmos. You're going to identify the real zeros on the graph and plot those in the lab. Then you're going to plot your y-intercept and make sure you've chosen the correct shape to connect the dots. If you were doing this by hand, you would then test the points, which is going to be important in the next one. So how do I find the possible rational zeros? Where am I getting that from? So if you look in the textbook reading, there's a reading on the rational root theorem, where you're taking the number in front of the highest exponent and the constant value, and you're finding all the factors of those numbers. Then you're dividing those. So the factors of 6 and 2 would be 1, 2, 3, and 6. So then I can have 1 over 2, 1 over 1. I can have 6 over 1. I could have 3 over 2. So when I'm doing this, I'm taking the factors of the 6 and I'm dividing them by the factors of the 2. And since the factors of 6 are 1, 2, 3, 6, then I'm going to have those factors divided by the factors of 2, which is 1. So then all of them divided by 1, and then divided by 2. 6 divided by 2 is 3. That's why you don't see that one there. So you're taking the factors of the constant, dividing it by the factors of the coefficient. You could check that using synthetic division. Once you get that factored out, you could do the step, which you guys are going to use Desmos.com. You're going to find those values on Desmos. And then there are your zeros. If you're not sure if something is 1/2, if you know the zeros are 2 and -3, you can do synthetic division twice, and that would tell you the 2x plus 1. Then you're going to plot your x-intercepts, and you're going to test. So this is if I'm not using Desmos, notice what they're doing here. They're plugging in values and finding if they're negative or positive. So this is going from negative to positive on the y value. So it's going from below the axis to above it. It's going from above to below and below to above. So if I graph this in Desmos, it's going to model that behavior. So for x-intercepts, zeros, and solutions, if I plug a value in and I get 0 out, it is going to be a solution for it. Now, the intermediate value and boundless theorems are going to be something that's related to that behavior of that above and below behavior. What the intermediate value theorem says is if I have a positive y value and then a negative y value, somewhere on the x-axis between those y values, it had to cross. So there exists a x-intercept somewhere between that interval. So if I plug in, say, -4, and I get this positive value, I plug in +4 and I get this positive value, somewhere between -4 and +4, it had to cross the axis because I went from positive y's to negative y's. That's all that is. So what I'm doing here is I'm plugging in -1 and -2. I'm seeing at -1, the y values are going to be negative. At -2, they're positive. So the intermediate value tells me somewhere between -1 and 2, I should have a 0. The boundedness theorem says that if a polynomial has a degree that's greater than or equal to 1 and a positive leading coefficient, I can use synthetic division, and if C is positive, all numbers in the bottom row of the synthetic division are going to be non-negative. If C is negative, the numbers in the bottom row are going to alternate signs. So here I have -3, and I have the alternating sign pattern because it's -3. That's all this says. This isn't really assessed in the lab, but it is something that's somewhat useful. Now, for the zeros of the polynomial using the graphing calculator, we're going to use Desmos.com. So this is how you would do it in a TI handheld calculator. You would use the function calc, then 0 or root. In Desmos, all you have to do is zoom in and click on where you think the intercept is, and it will tell you. So Desmos is a little bit easier to utilize for this. And see, the great thing about Desmos is you don't get this 1 e to the negative 12. It's going to tell you 0. So Desmos is a little bit improvement from this. Just make sure you're clicking and you've zoomed out so you can find all of the zeros. To use a polynomial function to model data, you would actually enter the points into Desmos.com and you could look at the actual model. This is not assessed in the lab. It's something we're going to go over really because this is a transformation utilizing the TI calculator. But it does do a good job of pointing out if this is all that I'm given is this upward curvature, this could be half a parabola. This could be half of a cubic because it could go down over here. Or this could even be a quartic because a quartic can be just the parabola as well. So when you're looking at those curved data models, you have a lot of options and you really need to break down what has this curved behavior, what could it possibly be? When we're looking at the r squared value, the closer r squared is to 1 in these transformations that you've graphed, that means the better fit it is. So if I'm looking for which one of these is the best fit, I would be looking for the r squared value that is closest to 1. Again, this isn't really something we're delving into this week because we've kept it pretty light so you can do your actual critical assignment.